But in case anyone wants to record, then I can allow you. I can always allow you to record your own. I can always allow you to record your own videos. I see only 4 people. I don't know where the 5th one has gone, but I hope others will be joining us. We can take like 3 minutes. Let's take 3 minutes and wait for them, just in case they are coming. I can't see where I can surely allow you to record, but ask to start video make host video. Report. Okay. I'll show you when I discover that technique, but I'm recording mine and I'll keep trying to see if I can share. Okay.
Okay.
Today we want to look at chapter 2 of linear algebra 2, and
okay, sir.
We will be looking at what we call the matrices of general linear transformation. Last time in chapter 1 we did, this is what we did in chapter 1. Now today we'll look at matrices of general linear transformations. We will define these matrices, and then we will see how to compute these matrices. Then we'll look at matrices of linear operators. We know that linear operators are special forms of transformations that are mapping elements within the same space. So after looking at matrices of linear operators, we'll look at examples and we will be done. So this is what the problem looks like. We have a linear transformation T, which maps things from vector space V to vector space W. V is an n-dimensional vector space and W is m-dimensional vector space. Now, if we have B and B prime as the bases for V and W respectively, we know that every vector space has got what we call a basis. And we know the criteria for a given set to be a basis for a given vector space. So since this V is n-dimensional and V is m-dimensional, then each of them have a basis. So the plural form of basis is what we are calling bases. So B is the basis for vector space V, and B prime is the basis for vector space W. For V and W respectively, then for each vector X in V, the coordinate matrix XB is a vector in Rn. What we are saying is that if this is X, then X should be n-dimensional. It should be n tuple, in other words, and if we can form this matrix, then it is a vector in Rn. Of course, we know any vector, if we write it in form of a column vector, then it becomes a matrix, because vectors are also matrices when you write them in column vectors. So this matrix is going to be a vector in Rn, and the coordinate matrix TB is a vector in Rm. You see, Tx is the image of this x, so it means the Tx is an element in W, and it will be in Rm. Okay, Irene, what are you saying?
Master, you've not shared the screen. We are not viewing it.
Oh, nice.
Really, I'm seeing it.
So
I'm not. I'm seeing your picture for Master.
Hey, you should be seeing a picture on a big screen. So just click on the picture so that it leaves the big screen, and then you'll be able to see the screen we are looking at.
Hey.
Are you now okay, Irene?
Yes, now I'm able to view it.
Okay, so this is what we are looking at. We are saying that if we have a vector V in V, then this matrix is a vector in Rn. In other words, it's n-dimensional. And when we transform it to Tx in W, this one will also be m-dimensional vector space. Okay, so it means we can find a map that takes things from Rn to Rm, which can be shown to be linear. That map can be shown to be linear, and it takes these vectors in Rm to these vectors in Rm. It takes xb from in Rn to Tx. This is the image of x. So if we let A, capital A, be a standard matrix for this transformation, then it means when we get that matrix times this, it takes us back here. Of course, every transformation, if it is linear, then it is associated to a given matrix A. So what we'll be looking at is finding this matrix A. And we want to label this equation 1. So keep in mind that this one is equation 1. Okay, so the matrix A in equation 1 above is called the matrix of T with respect to the bases B and B prime. Remember, B is the basis for V, B prime is the basis for W. Thus, we have the relation where we have this A, we can put TBB times this, it gives us that. Why? Because A is the matrix of transformation of T with respect to the two bases. So we write it like this, TBB, and we get this equation. Then, if we let the basis for V be this, V1, V2 up to Vn, and then the basis for W be W1 up to Wn, be the basis for the n, that we are looking for an m by n matrix. That matrix looks like this, such that equation 1 holds. What is equation 1? Equation 1 is telling us that when we get that matrix times any vector in V with respect to the basis B, it should give us this vector Tx in W with respect to the basis for W. So this is such that equation 1 holds for all basis vectors V1 up to Vn. And then, so it means that when we get this matrix times the first basis vector V1, we get, it should take us here, should give us this TV1, and when we get A times the second vector, it will take us here, and so on up when we get A times Vn, it should take us here. But we can use the standard. We know that V1b, for example, if we want V1, then we can always write it as 1, we can write V1 actually as 1 times V1, then 0 times V2. So we have written V1 as a linear combination, and so it means the matrix associated to V1 is 1, then the rest are zeros. Likewise, we can write V2 as a linear combination. We have a 1 here, so we have this. Likewise, we can write Vn with a 1 here. So that means when we get AV1 times this matrix, we get this. So this is what we are talking about, that the AV1 is a matrix whose dimension is m. So this is an m-dimensional vector. We can look at it as a vector. We can also look at it as a matrix. Okay, so AV1, remember, it takes us here, so it means the TV1 is that, and also A2, when we apply AV2, it gives us this m-dimensional also, so that one gives us the TV2. Likewise, AVN takes us here, so we have that, and finally, this shows that the successive columns of A are coordinates of matrices of this form. There is a close bracket here, close bracket here, close bracket here. This is a typo with respect to the basis. So this shows that the successive columns of A, the matrix that we get, will be coordinates. There will be coordinates of matrices of this, and that. And thus, the matrix TBB, which is A, which we are interested in, is going to be, which is the column. So we get the column here and the column here, so they give us what we call that matrix. In the case where V is W, so that TV, so we get a linear operator, and so if it is a linear operator, then the basis is the same. So we have only one basis because we are in the same vector space, so the basis is the same. So if that is the case, then we have only TB instead of TBB. Right now we have B.
Yeah,
so
you can pray for us and start.
B, and it will give us the matrix that we are interested in, and that is equation 2. Okay, so that is, I've explained the matrix of general linear transformation. Just in case anyone has a question.
Okay, let me pray.
In case anyone has a question, please feel free to ask me before we go to
Father, we
examples.
thank you for this wonderful morning that we are going to study something. We pray that you go with us and that we are going to share. We thank you, bless your name in Jesus' name. Amen. So, good morning once again. So, we are trying to continue. Bashir, yeah, how are you?
Any
Bashir?
question, please? I'm waiting for questions in case
Bashir, how
there
are
is.
you?